Hey, this is Horner. We're going to look at the next section. This is going to be inductors and inductor circuits. So it's part 4 of AC circuits. So this is a good review of what an inductor is. So we know that a changing current through a solenoid, so remember solenoid is just a piece of wire that's been wrapped in a coil, induces an EMF or a potential across that coil. So we've got a magnetic field going through it, and not only is it just going through, it is also increasing. Uh, Remember, it needs to increase and or decrease in order for you to have any induced EMF. So in letter A here, we see that the increasing flux through the loop does cause an EMF to develop, and so by using Lenz's law, we see that the sign of the EMF is such to oppose that, and that increases the current as it goes through. And if I decrease the flux, the decrease in flux causes an EMF that further decreases the current. So as it moves back and forth, we end up getting this increasing and decreasing current in that inductor. So we did say that they're just coils. They develop a potential difference across if the current through it is changing. And so because the direction of the potential difference opposes the change in current, an inductor does resist changes to current that go through it. By looking at Faraday's law, so we talked about Lenz's law and Faraday's law, the voltage developed across that inductor is proportional to the rate at which the flux changes through the coil. And so we kind of looked at that earlier. We said that V is equal to the change in flux. So I think we said V, or you could probably most likely need to use EMF over the change in time. So that was the voltage, and that's Faraday's law. So because that flux is proportional to the coil's current, the instantaneous inductor voltage, so here we go again, we're going to do instantaneous voltage across the inductor, so that's this, must be proportional to the rate at which the current through the inductor changes. So here's the current, and then there's the change in time, and then there's a constant, and that constant of proportionality, L, is the inductance itself. So whatever the inductance is of the inductor, then we have that constant there. So pretty simple thing to do. So the units of inductance, remember we said is a Henry in honor of Mr. Henry, Joseph Henry, the early investigator of magnetism. And that's also equal to a volt times a second per amp. And so that would be a Henry, capitalized letter, but it is not over here, as you see. The instantaneous current through the inductor, so we know VL is equal to the value of L for the inductor times the change in the current that's going across it over the change in time. And so in a simple inductor circuit, the inductor is in parallel with the source. So the inductor voltage equals the EMF. So here's our source, cosine of 2 pi f, so that's our angular frequency again, times time, and that would be the instantaneous voltage or potential across that inductor. Here is the picture or the graph that shows you what's happening. And remember we said that in AC current, the voltage and the current are in phase. We said that the capacitance in one of these circuits will go before the voltage, and so for the inductors, the AC current through the inductor lags the voltage. So you'll notice that should happen. So here, when our instantaneous voltage across the inductor is very large, then we have zero current. So that's when we have that current is changing very rapidly. When it's not changing rapidly, then we don't get any voltage there. And here it's changing very rapidly again. You've got the steepest slope here, so our voltage is at a maximum down on the bottom, and then back and forth. So that is how it behaves as it goes through. So let's do a little quick check here. It says in the circuit represented by the graphs, the current does what? And it does lag the voltage. So the current lags the voltage. Inductive reactance. So remember we had capacitive reactance. We also have inductive reactance. So we find that the relationship between the peak values of the inductor's current and voltage in the same way we found the relationship for the capacitor. So we're going to do the same thing here. Here's the voltage across that inductor. It's not instantaneous, that's the peak value. That's equal to the L value, that constant for the inductance, times 2 pi f times the current across that inductor. So this is what we end up with. We can rewrite this. It's very similar to what we had for Ohm's law, where XL is going to be our inductive reactance. And so you see here's your equation for inductive reactance. They want to know which current is changing more rapidly. So here I have a 2 Henry 2 volt inductor. Here I have a 1 Henry 4 volt inductor. And the one that is changing more rapidly is going to be number 2. And it's because I'm going to have this change in potential across the inductor is equal to negative L times the change in the current over the change in time. So the current here is changing more than it is on this one. The graphs of current and voltage are always sinusoidal, and that's what we said for a resistor. So we're kind of just going through and putting everything together now in these elements. So if I have a resistor, we notice that the voltage and current are always in phase. If we look at a capacitor, we see that they're not in phase and that the current leads the voltage. And then in an inductor, the current lags the voltage. And that's the difference between the two. The peak values of current and voltage are related by the resistance or the reductance. So here it's resistance for a resistor circuit. For capacitor circuit, it is that capacitive reactance. And then for the inductor, it's the inductive reactance. And so you kind of see what's going on with it. If we go ahead and switch this here, R is a constant. Resistance is a constant, but capacitive and inductive reactance will vary with the frequency. So we see those equations that we have here. And then this is a good problem. We're going to find the current and voltage of a radio's inductor. So we've got a 0.25 microhenry inductor, so times 10 to the negative 6. It's used in a FM radio circuit that oscillates at 100 megahertz. The current through that inductor reaches a peak value at 2 milliamps at 5 nanoseconds. So they want to know what is the peak inductor voltage and when closest to the 5 nanoseconds does it occur. So lots going on in this problem. So let's go ahead and we see that the inductor in the circuit is driven at a certain frequency. So we had that figure that we looked at, the synthesis figure that we saw earlier. So let's go back to it. Is this one. Oops, for an inductor. So here's our synthesis. We see that they're off by about 1/4 of a wave. And so that's what they're talking about here. When we see the inductor current lags the voltage reaches its peak 1/4 period before the current does. So that's what they're essentially meaning by lag. The inductive reactance at 100 megahertz is 1 times 10 to the 8th hertz. So, or you can do 100 times 10 to the 6th. It's up to you. So here's our inductive reactance is equal to 2 pi FL, 2 times pi. Here's our frequency. And then our value for L for the inductance was 0.25 microhertz. So that's times 10 to the, microhenries times 10 to the negative 6. So we get 157 ohms for that one. The peak voltage is I times X, so we find out that it's 0.31 volts, and that voltage peak occurs 1/4 period before the current does, and we know that the current peaks at 5 nanoseconds. So the period of that 100 megahertz oscillation is 10 nanoseconds. So the voltage will peak at a time where we have 5 nanoseconds minus the 10 nanoseconds divided by 4 because of that 1/4 period. And so we end up with 2.5 nanoseconds. And that would be the time that the voltage will peak. Next thing we'll look at is oscillation circuits.